Imagine a world with no friction, a world where energy could flow forever without losing any of its power. This isn't just a fantasy, it's a reality found in the strange and beautiful realm of superconductivity. At its heart, superconductivity is a property that some materials gain when they become incredibly cold, close to the coldest temperature possible, absolute zero. When this happens, something magical occurs. The material suddenly loses all its electrical resistance. It becomes a perfect conductor of electricity, a flawless highway for energy. This phenomenon is one of the most profound discoveries in physics, showing us that the universe at its most fundamental level can be surprisingly perfect and orderly. So, what makes these materials so special? It all comes down to the behavior of tiny particles called electrons. Normally, electrons moving through a material bump into things like atoms, which creates resistance and wastes energy as heat. But in a superconductor, the cold temperature allows the electrons to do something extraordinary. They pair up, forming what are called Cooper pairs. These pairs don't act like individual particles anymore. Instead, they move together in perfect harmony. They behave as one single, giant quantum wave, flowing effortlessly through the material without any scattering or collisions. This collective dance is what eliminates resistance entirely, allowing electricity to flow without end. This quantum behavior gives superconductors other amazing properties too. For example, they can completely repel magnetic fields. If you place a magnet above a superconductor, the magnet will float in midair, suspended by an invisible force. This effect, known as the Meissner effect, is a stunning visual demonstration of the quantum world at work on a scale we can see and touch. It's as if the superconductor creates a perfect shield, refusing to let the magnetic field pass through it. This strange and wonderful property is not just a curiosity. It opens up possibilities for new technologies that seem to come straight from science fiction. The discovery of superconductivity was a gateway to understanding the deep, hidden rules of the cosmos. It showed us that under the right conditions, the messy, chaotic world we experience every day can give way to a state of perfect order and efficiency. It's a glimpse into a different kind of reality, one governed by the elegant laws of quantum mechanics. This simple principle, of electrons pairing up and moving as one, is the foundation for some of the most advanced and mind-bending technologies we are developing today. It's a reminder that the universe is full of wonders, waiting to be unlocked if we just look closely enough. Now let's take this idea of perfection and apply it to building new things. Imagine you could design a material from the ground up, telling it exactly how to behave. This is the core idea behind metamaterials. These are not materials you dig out of the ground. Instead, they are man-made structures, engineered with patterns and shapes smaller than the wavelength of light or other electromagnetic waves. By carefully arranging these tiny structures, we can give the material properties that are impossible to find in nature. Think of it like building with Lego bricks, but on a microscopic scale, to create materials that can bend light in unusual ways or manipulate sound. So, what happens when we combine the perfection of superconductors with the clever design of metamaterials? We get something truly revolutionary. We create superconducting metamaterials. By making the tiny building blocks of our metamaterial out of a superconductor, we can harness its amazing properties. The most significant advantage is the elimination of energy loss. In normal metamaterials, the metals used to build them have resistance, which means energy is wasted as heat. But with superconductors, there is no resistance. This means our engineered material can guide and control waves with almost perfect efficiency, opening up a whole new level of performance. The benefits don't stop there. Superconductors also offer an incredibly strong response to electromagnetic fields. Because the electrons move so freely, they can react powerfully and quickly, allowing us to manipulate waves with unprecedented precision. Furthermore, these materials are tunable. We can change their properties by slightly adjusting the temperature or applying a magnetic field. This gives us a dynamic level of control that is difficult to achieve with conventional materials. It's like having a material with a built-in control knob, allowing us to fine-tune its behavior in real time for different applications, from advanced communication systems to powerful sensors. In essence, adding superconductors to metamaterials is like upgrading from a standard engine to a high-performance futuristic one. We are taking the clever designs of metamaterials and powering them with the flawless efficiency of quantum mechanics. This combination allows us to create devices that were once thought to be impossible. We can build circuits that don't lose energy, lenses that can see details smaller than the wavelength of light, and perhaps even materials that can make objects invisible. This fusion of two cutting-edge fields is pushing the boundaries of what is possible in materials science and engineering. To understand how these amazing materials work, we need to look at their fundamental building blocks. These are called meta-atoms. A meta-atom isn't a real atom like hydrogen or oxygen. It is a tiny, engineered structure that is designed to interact with electromagnetic waves in a specific way. Think of them as artificial atoms that we can design ourselves. A simple example is a tiny ring with a small gap in it known as a split-ring resonator. When an electromagnetic wave passes by, this tiny structure can resonate, storing and re-emitting energy in a very particular manner. It acts like a tiny antenna that we can control. By arranging millions of these meta-atoms in a repeating pattern, we create the full metamaterial. The collective behavior of all these tiny structures is what gives the material its overall extraordinary properties. For example, by designing meta-atoms that bend light backwards, we could theoretically build an invisibility cloak. By using superconducting meta-atoms, we can make these structures incredibly efficient. They can guide electromagnetic waves along a specific path with almost zero loss. This is crucial for applications where preserving the strength and integrity of a signal is paramount, such as in ultra-sensitive detectors or advanced communication networks. The real magic happens when we realize we can control these meta-atoms. Because they are made from superconducting materials, their properties are sensitive to their environment. We can tune their response by gently changing the temperature. A slight increase in temperature can change how the superconductor behaves, which in turn alters the properties of the meta-atom and the entire metamaterial. We can also use external magnetic or electric fields to achieve the same effect. This tunability means we can create dynamic devices that can adapt and change their function on the fly, moving us beyond static materials to active, reconfigurable systems. This ability to control the flow of energy at such a fine scale is a game changer. It allows us to build new kinds of technology for processing information. Imagine circuits that can be rewired with the flick of a switch, or antennas that can change the direction of their beam instantly. These compact meta-atom structures, powered by the strange rules of the quantum world, are the tiny engines that will drive the next wave of technological innovation. They are proof that by understanding and engineering the very small, we can achieve very big things, transforming how we interact with the world around us. We are now standing at the edge of an even more profound frontier. What if we could take the idea of a meta-atom one step further? Instead of using a simple metal structure, what if we used a true quantum object as our building block? This is the breathtaking concept behind quantum metamaterials. In these materials, the meta-atoms are replaced by artificial atoms, such as superconducting qubits. A qubit is the fundamental unit of a quantum computer, a tiny circuit that can exist in a superposition of states, both on and off at the same time. It is a pure quantum system that we can build and control. By arranging these qubits into a lattice, just like the meta-atoms in a classical metamaterial, we create something entirely new. We create a material whose properties are governed not just by its structure, but by the collective quantum state of all its artificial atoms. This is not just an improvement on existing technology, it is a doorway to a new kind of physics. These quantum metamaterials could exhibit bizarre and wonderful phenomena that have no equivalent in the natural world. They could allow us to create and manipulate quantum states of light and matter in ways we are only just beginning to imagine. The potential applications are staggering. Quantum metamaterials could become the backbone of future quantum technologies. They could be used to build powerful quantum computers, creating the perfect environment for qubits to interact while being shielded from outside noise. They could lead to secure communication networks that are impossible to eavesdrop on, using the fundamental laws of quantum mechanics to protect information. We might even be able to create new types of sensors that can detect tiny gravitational waves or the faintest magnetic fields, allowing us to explore the universe with unprecedented sensitivity. It's a technology that could redefine our relationship with information itself. As we stand here on June 15, 2025, we are witnessing the birth of a new field that bridges the gap between materials science and quantum information. Superconducting quantum metamaterials represent more than just a scientific curiosity. They are a platform for discovery. By learning to build matter atom by artificial atom, We are not just engineering new devices, we are learning to speak the fundamental language of the universe. The journey ahead is long, but the promise is immense. These remarkable materials could unlock a future where the strange rules of the quantum world are harnessed to solve some of humanity's greatest challenges.